Okay. Right. Hello, everybody. That was a very nice introduction. Thank you very much. Hopefully, over the next 50 to 60 minutes, I can talk about deep geothermal, one aspect of the many different things that I have done. Let's press the button. Nothing happened. How do we move forward? Okay. So you've heard a bit about me. Here's a bit more about me. PhD at Leeds University. Very nice trip to Costa Rica. I can thoroughly recommend it. I've been at BGS for about 35 years, senior geochemist. Really what connects all the work I've done is looking at the directions, rates, magnitudes of fluid rock reactions over a real different sort of range of temperatures and pressures. Oddly, I manage the BGS hydrates and ices laboratory, which is where we look at low temperature processes, strange ice-like phases that are called gas hydrates that you find in deep ocean sediments or below permafrost. But I'm also heavily involved in another lab next door, which is the hydrothermal laboratory, where we look at high temperature processes. And I'm winning projects, conducting research, supervising staff and students, sweeping the floor, bit of everything really. And I apply that knowledge to geothermal, which I'll talk about, storage of carbon dioxide, hydrogen, heat, disposal of radioactive waste, cementitious reactions, very highly alkaline environments, strange chemical environments that we find in various parts of the world, gas hydrates, and that monitoring. I've also got various activities outside of work. In Nottingham, archery, of course, very suitable for Nottinghamshire, which I do. I do a lot of wilding activities outside of BGS and within BGS, looking after wildflowers and the orchids that we have growing here at BGS, and oddly, beekeeping. I'm the official BGS beekeeper, and we do make BGS honey available to all good retailers. So anyway, back onto the presentation. It's a three-part presentation. I'll give a bit of context first about low CO2 technologies and what is geothermal, and then focus in on Southwest England in particular and tell you what's going on there. It'll include Eden and lithium extraction from the waters, and then move into the crazy world of the hottest of the hot, where we talk about sort of international projects to access these super hot fluids. And this is sort of where some of the leading edges of research is at the moment. So context, where are we? What's the global context in this? Well, it's CO2 emissions. The CO2 emissions are going up, and we've got to change our energy generating technologies. And the UK is committed to a 78% reduction in CO2 emissions by 2035 as compared to 1990 levels. Until recently, it was 40%. That commitment has gone up. And we are committed to net zero by 2050. This is kind of a really big challenge. And when we look at how CO2 has varied over time, which is the diagram on the right, which from the left goes to from 450,000 years ago, and on the right-hand side is today, and the vertical axis is CO2 mixing ratio from 170 parts per million at the bottom to 370 parts per million at the top. And over the past few 100,000 years, you can see the CO2 concentration go up and down in the atmosphere as we swing in and out of glacial cycles. There being more CO2 in these glacials. And on the far right-hand side, you can see the current blue line, the higher level of CO2, and then a vertical red line, which is the human bit. That short period of time that we've been large amounts of CO2 into the atmosphere.
Do it again. I like to do things, and then I can do them.
We have a bit of if somebody's got that,
pretty sure
possible to turn.
When we were setting things up,
no,
we did get through.
Carry on. The CO2
online using my card
are going up. When I was
not long after you used bought your iPad.
Parts per million. When I started my research, it's more like 350 parts per million. Today, we're almost up at the top of the diagram at, well, today was 3 days ago, 430 parts per million nearly. And before we know it, we'll be off the top of the plot over 450 parts per million. The rise is absolutely huge. And what I find most frightening is that just in my lifetime, and I'm 60, the amount of CO2 increase is as much as an entire 100,000 years glacial cycle. So we are belting out an awful lot of carbon dioxide into the atmosphere really, really quickly. So we've got to do something about this. And the UK has been reducing its emissions, thankfully. And in 2023, total emissions about 380 million tons of carbon dioxide equivalent. That's gone down by about half compared to 1990, which is a really good and positive step. And we see these numbers reducing over time. The next 50%, though, that's going to be difficult. The first 50% is easy by comparison. This is where we've got to bring in new technologies for providing heat and power. Not all will tackle our total greenhouse gas emissions. We talked about agriculture and things like that at the start, but let's see what we can do for the bits that we can do from the geological perspective in terms of energy and reducing the CO2 from that. So if you think about geothermal energy, it's that part of the Earth's heat that we can or could be recovered and exploited. Now, the Earth's pretty hot, and a lot of this heat is generated through radioactive decay of elements such as uranium, thorium, potassium. And as we go deeper, it gets hotter, and going down to 100 kilometers deep, we're talking about temperatures of 650 to 1200 centigrade. And at the core of the Earth, center of the Earth, it's more like 6,000. And some 98% of the Earth is greater than 1,000 centigrade. And we just inhabit this thin veneer on the outside where less than 0.1% is cooler than 100 centigrade. So as this heat migrates up from the center of the Earth, can we utilize it? Now, if we visualize geothermal, we think of things like steam vents, geysers, fume rolls, maybe mineral terraces that you might see in Turkey or New Zealand, vents with sulfur growing around them. And in these hot areas, there you can visualize this magma chamber providing heat, which heats up the groundwater and gives these sort of visual indications of geothermal being present. But we don't have that in the UK. We do not see this at all. We don't have that level of heat. We are much cooler. And the sort of things we have in the UK, and this little diagram from the left, we can think of shallow systems, which may be a few tens of meters deep, ground source heat systems, where you can maybe extract some heat energy from shallow aquifers at maybe 10 to 15 centigrade. If we were to go deeper, say mine water energy, you may be sort of getting in the 20s centigrade or so, and you'll be down a few hundred meters in the old mine workings, flush water through those and extract heat from that, and concentrating it up and using it in buildings. If you go deeper still into deep aquifers, where you could be talking 2 to 3 kilometers deep maybe, access much warmer water, 60, 70, maybe 80 centigrade water from deep aquifers, and use that direct heat use in for heating buildings. And then go deeper still, which I'll talk about perhaps a bit more, go down maybe 5 kilometers into fractured crystalline rock at depth, granites, for example, and access temperatures well over 100 centigrade. And this hot water we could extract is really important in terms of heat use if we can do it, because over half of the UK's energy is used actually for heating the buildings. I should say for granite, we can maybe go even hotter still, because in Cornwall, we're looking at temperatures more like 190 centigrade at 5 kilometers depth. But more about that in a moment. But we've been utilizing heat in various ways, where there are warm springs. The Romans came and built their baths and been utilizing it for a long time. Even today, if you go down to Penzance, is the Jubilee Pool, where there's a part of it is heated by a heat exchanger with geothermal water from a nearby borehole, and you can enjoy geo and fizz if you wish to pay for the tickets whilst sitting in the water of the pool. Other countries with higher temperatures can put on geothermal power plant with these sort of temperatures and flash the water to steam. We do not have temperatures quite like that. And we have to think about extracting heat energy in a different way if we want to generate electricity from it. And I'll introduce that in a moment. Shallow ground source heat pumps, they effectively work if they're really shallow, just laying pipes in the ground, covering them with earth, and they pick up small amounts of heat from the ground. And really, you can pass that through a heat exchanger, perhaps generating water up to 40 to 45 centigrade. It limits their application to low temperature heating systems, such as underfloor heating within buildings, to give that sort of general warmth within the building. Whereas fossil fuel boilers for like radiators and that, you'd need to, they heat the water to 70 to 90 centigrade. So you'd have to boost the temperature from ground source heat pumps if you wanted to use those in the same way. Although it does save quite a bit of energy if it's already preheated the water from a ground source heat pump. Effectively, the way it works on this diagram on the right-hand side, you have a heat loop outside. The water is pumped through a heat exchanger, which has then a refrigerant type material in a compressor. And that sends the heat to a second heat exchanger, which goes into the domestic heating system, normally underfloor heating, potentially if it's hot enough, cylinders and radiators, but you might need to boost that temperature with a small conventional boiler. If we were to go deeper, and I said we have deep aquifers that we can exploit, well, in the UK, there was a project in the 1980s to look at the deep aquifers and what their geothermal potential was. And typically they're permo-Triassic sandstones, maybe 1 to 2 kilometers deep. And we have some really nice basins, the east of England, Wessex, Worcester, Cheshire, one in Northern Ireland as well. And those have a large amount of heat in place. I've done this in exajoules, which is a very large number, but it's effectively millions of barrels of oil or tons of coal equivalent worth of heat in the hot water in these basins. And if you could drill down to them and extract the water and heat buildings, then you can utilize that. Unfortunately, some of the basins don't lie where there are cities nearby, but one of the boreholes in Southampton from the geothermal exploration program was used as part of a district heating scheme. And that's worked off and on for quite a few years now. I'm not quite sure if the pump's working anymore. The problem is exporting that heat needs a heat network to the surrounding buildings. And we haven't in this country put heat networks in place so we can connect houses up. A lot of other countries have this under the roads in place, and it's easy to export this heat to houses. Unfortunately, in the UK, we'd have to lay an awful lot of new pipes to allow that to happen. If we go deeper still and think about deeper geothermal in the UK, and focus on the diagram in the middle, which is the heat flow map of the UK. Most of the country's green, patches a bit of blue, a few patches orange, a little bit in the East Midlands, a chunk in northern England. But Cornwall and Devon stand out as like kind of big bullseyes of heat flow where the granites are. And a colleague modeled temperatures at 5 kilometers. And you're sort of getting approached to 200 centigrade in these granites in Cornwall. And South of England stands out because it's underlain by radiogenic earlier Permian granites. They're relatively old, but they're slightly enriched in potassium, uranium, thorium, and natural radioactive decay has raised the temperature of these granites enough to make us significant temperatures at depths which we can actually drill to. And the heat flow is about 130 or so milliwatts per square meter from these granites, relatively high heat flow. And these are the targets for geothermal exploration now in southwest England. So the work started quite a few years ago. There's a hot dry rock geothermal program centered around the 1980s, but it followed on from research in New Mexico by Los Alamos National Lab looking at hot dry rock systems. And the Rose-Manoas Quarry was chosen, which was the focus of the UK project, led by the Camborne School of Mines, BGS and other universities also involved in 3 phases from the late 70s to the very early 90s. And in today's money, you're probably talking about 200 million of investment in research. It was a hot dry rock study in granite. It was away from main big fracture zones. It was a relatively intact block of granite, but they wanted to create this fracture network. They fracked the rock in places. They also sheared the rock in places. And they, via 3 deep boreholes between 1.7 to 2.6 kilometers deep, and they were trying to create a fracture network around the boreholes, which they could circulate fluid through, which they did. They created this network and they tested it at a reasonably large scale. They extracted heat. The water would come up at about 100 centigrade. But over time, the connection was too good, and the system did start to cool down. They really needed to go deeper to kind of generate the hot temperatures that they wanted. Apologies, I should have said where this quarry was, Rose-Manoas Quarry, top right there. It's in the Carn Manellis granite, not far from Falmouth. And just above it is a star marked UD, which is United Downs, which I'll mention in just a moment. Now, the hot dry rock project had modeled the temperatures down to 7 kilometers, where they were hoping to get 250 centigrade fluids, and they had to apply for funding for this, and the UK government wouldn't provide the funding, and unfortunately, the program collapsed, and the work moved to Europe. Expertise was lost to Europe. People went off and did other things. Some of the knowledge was retained and fed into radioactive waste and oil and gas programs. So unfortunately, that was it for about 30 years, and we were in the doldrums for quite a long time. But these very same fractures of the fluid flow properties for geothermal exploration. So Cornwall is full of fractures. Any of the mineral veins are roughly oriented northeast, southwest, or east, northeast, south, southwest, across the whole of Cornwall and parts of Devon, broadly speaking. And the miners exploited these. And as they were exploiting along the mineral veins, they find the mineral veins would stop. There was something cut across the course of the mineral vein, and it was jogged sideways. And the miners cause these structures cross courses. And as well as causing them problems following the mineral veins, they conducted a lot of water underground, and flooding in the Cornish mines was always a great problem and led to massive developments in steam power and pumping of water from mines. These cross courses go roughly northwest, southeast. And if you look at large parts of Cornwall and Devon, there are an awful lot of them. They tend to occur in clusters, these fracture zones, which may be 200 to 300 meters wide. And on the top right-hand diagram, Chris Yeomans tried mapping out some of these for just the Land's End granite. And you can see these green lines across the tip of Cornwall, the tip of Land's End granite. And you can trace them offshore by using bathymetry. So these are relatively large structures. They have long distances. And it's these structures, the larger ones, built of hundreds maybe of individual fractures, that are the targets for geothermal exploration. So the in situ stress orientation allows fluid flow along these northwest, southeast features, whereas the original mineral veins, if you like, are sealed up and there's no flow along those. And they have good permeability. And the hot dry rock project, using its microseismic data, showed that when they injected water, it tended to migrate downwards, down features. And this helped underpin the concept of what's called the United Downs Deep Geothermal Power Project. They have a shallow injector, maybe down to 2.5 kilometers, and then a deep producer, maybe from 4.5 to 5 kilometers, producing the hot water, and run this system as a doublet, accessing relatively steeply dipping fracture zones. And the one they're targeting is called the Porthtown Fault Zone. And these are natural fracture systems, there's no hydrofracking, that will hopefully exhibit high enough permeability to allow circulation. This is what's been targeted at the place called United Downs, which is the one star on the diagram at the bottom, which says UDDGP, the United Downs Deep Geothermal Power Project. And then the Eden project, accessing the St. Austell granite. So I'll talk about United Downs project first. It really does build on the knowledge from the hot dry rock project. Some of the same staff are involved, the few that hadn't retired. And it was basically a long-awaited second phase of the work. And it is creating the first geothermal power plant at a demonstration scale. But it will produce heat as well. It's at an industrial site near Redruth, and it has links to a lithium extraction plant on the same site. It's run by Geothermal Engineering Limited, and a range of different funding to get the system working. But associated with it have been several science projects, which is where I get involved. A lot of them are European funded, some of them UK funded or partly UK funded. It was a great project to get started, but gaining public acceptance is one of these really big issues, and a lot of work was put on. And early on, a community liaison group was formed with lots of meetings, including web-based ones with the local people and the councillors. These are still happening even today. a lot of outreach to local people with open days, come and speak to an expert, programs for school children. Miss Molecule was invented as a game-based learning thing for primary school children about how heat moves. And then for secondary school kids, there was work with Raspberry Shakes, which was little Raspberry Pi computers with a motion sensor attachment to them to explain microseismicity and the monitoring that's going on. And those worked surprisingly well. But there was also symbolism. The Cornish flag was put on top of the drilling rig. There's lots of Cornish people are very kind of independent in their thoughts. And they quite liked the flag. An interesting story was it one gale, it blew the flag off the top, and the locals complained they'd lost their flag from the drilling rig. And one of the drilling engineers had to shimmy up the drilling rig and put it back on again to keep them happy. So they kind of accepted the drilling rig, which was really rather nice. It was their drilling rig, it was their project. Slightly more technical diagram of the United Down system on the left, if you can see it. The grey line is the steep dipping Portown fault zone, and then the shallow injector, which is UD2 well, which it has a measured depth of 2,393 meters, but because it's deviated, the true vertical depth is only about 2.2 kilometers. And then there's the UD1, which is the UK's deepest onshore borehole. It's 5,275 meters long, true vertical depth of 5,057 meters. And it'll be from that deep well that heat will be produced. The top kilometer of these boreholes is in through Devonian slates, and then the bottom 4 kilometers of UD1 anyway, it goes into granite. And to put it into context, the deepest mine in Cornwall, Dolgarth mine's about a kilometer deep. Burj Khalifa in Dubai is 830 meters tall. The Shard's only 310 meters tall. So they're tiny little grey pimples at the top compared to the depth that they're going in this borehole. Now, drilling was done in 2018 to 2019, and the boreholes at the surface are about 8 meters apart. They were targeting the hanging wall of this fracture zone, which is kind of important to note that going from above, if you like. And when they were drilling, when they would lose the drilling fluid, they know they were indicating flow zones. And we collected drill chippings, and some of these are now, well, all the ones I could get are now in the national collection. There was no standard coring. It was all done on drill chips and caliper and image logs down the borehole to work out where the fracture zones were that they could use. The bottom kilometers kind of is open hole to try and access as many of these fractures as possible. There was a European project that did come along and take some sidewall cores because they had lots and lots of money. Samples went to Germany, and unfortunately, UK researchers never got sight of them. So we've had to do all the work we can from the image logs and sort of drill chips, which has been a little limiting. The first phase of the work was really to understand the nature of the reservoir, and a lot of microseismic monitoring was done. Both GEL had monitoring stations, and so did we at BGS. We ran ours through COVID, and we just kind of left them there for 2 years because we couldn't really get into the field. And then there's been several water production tests. And the first big one in 2021, it was producing water at over 100 centigrade at the surface. So it was kind of boiling. And it was flashing to steam. And when you were listening to the thing, the water was going into this big steam separator, and steam was coming out of the top, and water was going into a big pond. And it was really quite nice. And I was amazed by this. I waited years to see this. But that's not as long as, if you like, the UK has waited for boiling water at the surface. Hasn't happened since there was probably last volcanism, which was about 52 million years ago in northwest Scotland. So this was really quite an incredible event, ignored by most people, but I find it very exciting. But these fluids, when they come to the surface, also contain lithium. And at about 250 parts per million, that is really quite useful in terms of separation potential. It's got low concentration of other elements, especially magnesium, which would get in the way of certain separation technologies. So as well as heat, we've got these minerals that we can maybe extract, dissolved minerals from these fluids. In terms of power generation, it's a binary cycle power plant, which basically means there's two fluids involved. If you look at the diagram at the bottom right, the production well produces the hot water, goes to a heat exchanger, and goes straight back underground. The heat is it captured in heat extractor by a second fluid. In this case, it's pentane, which boils at a lower temperature than water. And it's boiled off into vapor, which turns the turbine, powers the generator. And then the pentane is condensed using very large cooling fans and then fed back through the heat exchanger. Where the lithium comes in is at the cooler end of the water flow line, and they would intercept some of that water and extract the lithium using a range of ion exchange resins and similar. And the idea is to produce between 1 to 3 megawatts of electricity. The system is big enough for 3 megawatts. It's going to be switched on this year. They are testing parts of the system now. Maybe by September, it'll be the big switch on day. We'll have to see. It's more complex in terms of plumbing in real life, and an aerial image kind of shows it. You've got a range of different things amongst all that pipe work. In the middle of it all, there's hardly visible are the 2 big boreholes. They feed the hot water to heat exchangers with a turbine and generator in the middle. There's the part in green. The right-hand side, 2 little transformers to send the power out to a power line next door. And then at the back is what's really more visible is the cooling fans, a condenser to recondense the organic back into liquid form to send back through the system. So it's quite a compact site in the middle of this industrial estate. So that's the demonstration system. And Geothermal Engineering Limited have other interests. Clearly, there's the lithium that they want to investigate. They have planning permission for 2 new sites for geothermal power at places called Manhay and Penhallow, both down in Cornwall. And there's also a planning application in Tregarth, north side of the Bodmin granite. And they're likely to adopt similar borehole configuration to that at United Downs, intercepting a steeply dipping fracture zone, shallow water injection, deep water production. And they might produce about 5 megawatts of electricity. And they could sell heat and lithium. But it's going to take a lot of millions of pounds worth of investment to make this happen. And this is new exploration, really. We know relatively little about the rocks at depth here. So they're not quite drilling blind, but they're taking some large risks, certainly for the first borehole, when you're exploring these new areas. But it is very exciting. There was a question about geothermal at Eden earlier on. So Eden Geothermal Energy Project has received funding from a range of sources, EU, local councils, etc. And there's initially one single well, which is longer than 4.5 kilometers into the granite, the south side of the St. Austell granite. And the first phase is to produce heat for Eden's biomes, which is where things are at the moment. So on the top right is a picture during drilling. Below that on the right is a picture from about 2 weeks ago of the wellhead. And the borehole there, it's got a true vertical depth of about 4.8 kilometers, which is the 2nd deepest onshore borehole in the UK. And it goes down and it intercepts the footwall of the fault rather than the hanging wall of the fault. So it has more deviation on it than at United Downs, which means it needs a longer borehole. And it is actually 5,277 meters long, 2 meters longer than at United Downs. I think there was a bit of one-upmanship going on there, but it is the longest geothermal well in the UK. And again, I got a collection of drill chips and they're filed away in the national collection here at the BGS. So this first borehole at Eden powers 3 heat loops. There's the hot water from the borehole. It's brought up to the surface and fed through a heat exchanger, which is the size of a large container, really, shipping container, and that's then sent back underground. There's then a 1.4 kilometer heat main to take the heat to the Eden site itself, where there's another heat exchanger, and that actually sends the heat around the Eden buildings on the site, including the biomes. The Eden borehole in red there is north of the Eden site, which is in the bottom of the picture, and it's targeting something called the Great Cross Course, which is in yellow, those yellow lines on the map there, and it splits in 2. The Great Cross Course does, and the Eden borehole is just intercepting one leg, if you like, of that borehole, going into the footwall of that fracture zone. There was some flow testing in 2022. Didn't get great results, and that's why there's now a downhole heat exchanger powering the heat loops. But in the future, they want to sort of open up that EG1 borehole again, potentially drill a second borehole, try and connect the two or fluid flow between the two to have a doublet system and produce heat and maybe power. This is sort of a longer term aim if they can raise the finances. The third company in the mix down in Cornwall is called Cornish Lithium. And lithium has been known about for years. Even go back over 150 years, there was reports of dissolved lithium, lithia, in waters where there were springs into some of the mines. And Cornish Lithium are exploring shallower parts down to 2 kilometers to try and intercept any lithium resource in the area. And they might have about 100 parts per million dissolved in this shallower water. It's cheaper to drill shallow wells than really, really deep ones. So they're targeting a slightly different aspect of the fluids in southwest England. And of course, the fluids will be slightly warm, so they could maybe sell low-grade heat as well. Now, lithium was tracked back in the hot dry rock days as really a tracer. It wasn't thought about ever producing anything from it. And there was great interest in some of the mine springs seemed to carry 220 parts per million, relatively concentrated, very similar really in many respects to the deep water from 5 kilometers deep. And this lithium is coming from dissolution of micas, and in particular biotite, which carries several thousand parts per million in its structure. And so the one hypothesis we've got is that deep geothermal fluids rise along certain fractures from depth and only really get diluted in the top few hundred meters of the earth, quite close to the surface. And if you could intercept any of these fluid rising zones, then it'd be great for lithium, but they might also carry heat. So they're good targets, both geothermal and lithium, if you can find them. And we're trying to understand where these fractures are. And is there some sort of hydrothermal circulation system bringing water up in some places and it's sinking water in others? And we want to target these rising legs of the system for exploration. Cornish Lithium and GL have collaborated in the past on lithium extraction, but now they're setting up their own demo scale lithium recovery plants. Cornish Lithium have a planning permission approved for one, and the lithium that's produced perhaps could go to this battery gigafactory that they want to build. I think it's near Bridgewater in Somerset. So there could be local use of the lithium. But as you're extracting elements from this fluid, other ones you might also get could include rubidium, cesium, maybe silica. So we can extract as much useful stuff as we can from this geothermal water. And so alongside the use of heat, power, elements, there's a cascade of geothermal uses. And down at the bottom end could include spas, greenhouses, fish farms. Maximize the use from this hot resource from out of the ground. So to summarize, we've got Geothermal Engineering Limited, deep and hot, 2 boreholes, power generation is their main thing. They will sell some waste heat and dissolved lithium. Eden, it's deep and hot, 1 borehole for now, for mainly heating greenhouses, thinking about other applications if they can drill the other borehole. Cornish Lithium, intermediate depth, warm. They've got 8 boreholes, mainly lithium production, maybe some low-grade heat. Cornish Lithium also have a hard rock lithium production, as does British Lithium, again, feeding into this lithium pipeline that is beginning to develop in southwest England. So southwest England's really the leading edge. What can it mean for the rest of the UK? And a couple of colleagues some years ago tried to model temperatures at both 5 and 7 kilometers. And once you go down about 7 kilometers, large parts of the UK subsurface are getting into the 200 plus centigrade bracket. And 7 kilometers is quite easily drillable these days. And with drilling technology improvements, which is the really key thing we need, especially the rate of drilling, we could economically access some of these depths. And if you look at the power potential for these, as my colleagues did, they are estimating that at 4.5 kilometers, reservoirs greater than 175 centigrade might give you 2.2 gigawatts of energy, which is kind of a large power station, really. Go down to 6.5 kilometers, you're 100 times that. So, 100 power stations, big power stations, that's a lot of energy. And they then did a calculation for 9.5 kilometers. And if we ignore geomechanics, which is a big concern, But if it were possible to keep the fractures open at those sort of depths and develop just 2% of this enormous amount of energy, this huge number of exajoules down there, we could have over 1,000 times UK energy consumption in 2015 figures. So at depth is a fantastic resource. We've just got to be able to drill down there economically to tap into this. The big question, though, is, are there fractures open to allow fluid flow? And we really don't know that. And that's where a lot of the research is lying at the moment, to try and understand the stresses in the subsurface and the conditions in the subsurface. Are the rocks strong enough to hold fractures, which we would need to exploit? So that's the kind of the UK and where we currently are, and hopefully having an exciting future this year if we have a power plant switched on. What if we go even hotter? Where can we go overseas and look at more traditional geothermal power resources and they get into the really hot stuff? So other countries, yes, they have geysers and fumaroles and mineral terraces, and the locals kind of make use of this heat and enjoy it to keep themselves warm in the winter. But we can also exploit this heat, and using the heat that's flowing out from sort of magmatic bodies and warming hot fluids, can we tap into those in geothermal wells? Now, it started off a long time ago at a place called Larderello in Italy in 1904, where steam was used to light 3 light bulbs. And in those early days, things were kind of a bit on the edge, and health and safety matters weren't really thought about for these poor workers who were stood next to a discharging geothermal borehole, which would be like standing next to a rocket. They probably were deaf. But in these high temperature areas, typical, if you like, geothermal power plant were ultimately built in Iceland, Italy, New Zealand, places like that, using either dry steam straight from the ground or high pressure water, which is then flashed to steam and used in geothermal plant. And at the moment, if you look at the capacity around the world, we've got about 16 gigawatts. Relatively small number of countries really have most of the geothermal resources exploited at the minute. The US, Indonesia, Philippines, Turkey, New Zealand, Kenya, Mexico, Italy are the main ones, really. Indonesia has plans to maybe increase its geothermal potential massively in the next 10 years and overtake the US. So countries which are starting to exploit this are definitely making use of it, and they find their systems can help their countries economically and power-wise. Typically, what you're trying to do in these systems is access water, which will flash to steam when you bring it to the surface. Now, I don't want to go into the diagram on the left too much, but if we take the top left of it at the surface, down on the left-hand axis, down to maybe sort of 3.5 kilometers, where it's higher pressure, and the axis across the bottom goes from 100 centigrade to 400 centigrade, and a typical geothermal borehole follows the blue dotted line. It follows this curve in the near surface and then reaches a maximum temperature, which then carries down at depth. And the idea is that you can suck up water within this kind of blue dotted envelope, if you like. And when you bring it past something called the boiling curve, it will flash to steam. And that's what happens in a geothermal plant on the left. They produce the water, it's flashed to steam in the separator, that powers the turbines, and then the wastewater is either used for direct heat uses or re-injected. The diagram on the left, the black lines, it's called the boiling curve of water. And as you increase the pressure, as you go deeper, then the water boils at higher temperatures. And this carries on all the way up to a magical point called the critical point, which for pure water is about just over 370 centigrade and 220 bar pressure. And if it's a salty water, it's at slightly higher pressures and temperatures. But beyond these conditions, you enter something called the supercritical phase. There is no steam, there is no water, just a single phase. And these are kind of very strange kooky chemistry, changed properties of water. Lots of liquids do this. Water isn't the only one by any means. But those are the conditions for water. And if we go to super hot geothermal, we can start to exploit some of these really, really hot temperatures. The diagram on the right, the top left-hand part of that diagram is essentially the one you've just seen, where conventional geothermal is in this kind of 250 to 300 centigrade region, close to the boiling point, a boiling curve, of water. Super hot or super critical geothermal is the region beyond that critical point of water. For reference, Cornwall is the blue star. That's the United Downs, 5 kilometers deep and about 200 centigrade, well away from these really hot conditions that you might find above magma chambers. So superhot system, superhot is defined as above 350 centigrade. Supercritical, you're more or less kind of above 375 centigrade. These very hot boreholes could produce 10 times more energy per borehole than conventional ones. This is the big win. And so the Icelandic Deep Drilling Power Project, IDDP, was set up in 2000 to see if we'd actually do this in practice. And they've drilled several boreholes. The first one's at Krapla in the north of Iceland. The second one was drilled at the end of the Reykjanes Peninsula, not far from the main airport on Iceland. And they're planning the third one at Hengil, which will use new technologies. And other countries are also showing an interest in this, especially the US and New Zealand, which are putting in tens of millions of dollars into this sort of research. And so there's the IDDP-1 borehole, the top of it, to try and intercept this region above a magma intrusion at Krapla. Unfortunately, right above that intrusion, they found magma. They drilled into magma. It was a rhyolitic and more acidic composition. And that kind of confused everybody, and it was extremely exciting and very, very hot. And so IDDP-1 terminated early at 2.1 kilometers rather than the 4 kilometer it was aiming at. It hit molten rock and had a bottom hole temperature of 900 centigrade, which is a record. And the borehole did eventually cool and then started to produce fluid, superheated water at superheated steam, at 450 centigrade, which is another record. And they were getting huge amounts of this superheated steam. It was extremely powerful. They could barely deal with it. It was about a 30 megawatt equivalent borehole, 10 times the energy that we might get from Cornwall. That amount of energy is about enough for 60,000 Icelandic houses. And future wells, if they went to these super critical systems, could be bigger, up to maybe 50 megawatts of electric equivalent each. The Icelandic population for domestic uses only consumes about 150 megawatts electrical energy. So 3 of these big wells could power the entire population's domestic use. They're incredibly powerful, fantastic resource if we can actually manage to handle it. The problem is it was so powerful and the fluid so aggressive, it dissolved the inside of the borehole lining, which reacted with sulfur to produce iron sulfide particulates, which were blown out of the top of the borehole at the start, creating some sort of terrestrial black smoker, if you like. But once all that was flushed out of the system, it produced dry steam. The corrosion subsided, but it was extremely hot. And the metal expansion essentially damaged and destroyed the borehole, and it had to be abandoned in the end. They learned an awful lot about the engineering and the technical difficulties of handling these fluids. They also did lots of other testing, looking at erosion and corrosion, heat exchange of materials, scaling, lots of really useful things. It was a terribly aggressive, very powerful fluid that came out there. But it does open up this idea of magma energy. Could this be, if you like, holy grail of geothermal? Really, really high power with low gas emissions from a renewable resource. And there is an interest in the UK because Iceland is just about reachable with a subsea cable these days. To be a very long one, granted 3 times longer than what's been done at present, but it would be quite possible to send a power station's worth of energy to the UK from Iceland. It would be a bit of a capital investment to start it off, but the technology is there to do that. And this led to the idea of can we get geothermal and magma and understand how these systems work? And the big question for me in terms of geothermal and hydrothermal processes is what is happening above a magmatic heat source. As the magma freezes and just belts out all this latent heat, you create this supercritical resource above the magma chamber. Is that sort of controlled by the fact that there's no great fractures or they're small and you just can't get much fluid to the magmatic heat source? And the loss of heat from the magma is restricted by the restricted amount of fluids that are down there. And that fluid interacts with an overlying subcritical geothermal system and the mixing of waters. That's kind of one model of the system. Or is the system more like that right by the magma, the supercritical resource has massive permeability and it's dissolving loads of material and reprecipitating it in some sort of crispy candy shell around the magma chamber. And it's that physical barrier that separates a supercritical from a subcritical resource. We don't actually know, but I do think this second model better suits some of these systems that we are looking at, and that near the magma chamber, there is really, really high permeability. And if you can drill into that, you could get lots of fluid out. So what's happening above the magma chamber? Can we find out more about this kind of system? Previous people have made comments about what's happening on these volcanoes, and Hilary Price's Volcanic Insight is, I'm sure, very, very useful. But it does open up the possibility that there's not just one thing below volcanoes and calderas. There may be more than one chamber involved. And indeed, a lot of work is going on to understand calderas and caldera processes and unrest within them. And how do we model what's underneath them? The diagram on the left is an old model for, say, the Yellowstone caldera. Is it essentially one big blob of magma that's down there below the caldera? Or on the right, is it more like a great series, a great tree of different branches of magma chambers, different ages, different stages of evolution, different chemistries, from basic to more acidic? And this model is from the Los Humeros caldera in Mexico. And perhaps is a really complicated plumbing system under these calderas. And that's going to give a complicated flow system for geothermal resources. And we need to care about calderas because, as well as hosting all these resources, they're often associated with some of the largest and most destructive eruptions in the geological record. And we live amongst them here in Campo-Flagrange, Naples, with 1 million people living in and around calderas. And could monitoring technology, could drilling into them, help us understand them and even predict unrest within these systems? And of course, around Naples, the ground's going up and down like a yo-yo as different magmas injected, and there's episodes of magma degassing and these small earthquakes, and they come in these cyclic patterns over the years as there's a magmatic system is kind of breathing its day-to-day movement within these systems. So can we monitor this? Can we drill down and understand these systems? Because volcanoes can even impact the UK. If we think about the Eyjafjallajökull volcano and the ash plume that shut down European airspace and cost an awful lot of money. We can't stop these things, but maybe we can predict them if we understand more about the subsurface. And this is one of the aims of something called the Krabla Magma Testbed, which was devised some years ago, because Northern Iceland is only one of 2 places in the world where we know where there's unerupted magma at depths that we can drill and have drilled, which is just over 2 kilometers deep. The other site is in Kenya. And so if we had a project looking at this, we could get knowledge about the heat and volatile flow to better understand magma thermal energy, but also a detailed study of active caldera to better understand caldera unrest and volcanic hazards, and also recover core samples, the first core samples from gas-rich magma, which really is the hottest fluid that you are going to access via a borehole. And this really needs a coordinated effort and a large scientific community. And there's been a range of meetings and about this. We're trying to arrange effectively a £100 million science project. And it's really difficult to try and do, tying everybody together from around the world. So an interpretation of what we might have at Krabla would be at the bottom, a basaltic magma chamber at maybe 1300 centigrade, and heat from that heats the overlying hydrated old lavas and sweats out, if you like, a rhyolitic magma at about 800 to 900 centigrade. And it's that in which IDDP-1 intercepted, which is the black vertical line. Other boreholes from Krabla, the blue lines, nearly intercepted that magma chamber on previous occasions. And what we think happened in IDDP-1 is that they were drilling down nicely, the central part of the diagram, drilling down nicely at about 350 centigrade, got down to about 2,070 meters. Some discussion that they maybe went through a slightly crunchy, harder zone, but certainly then they lost all the fluid circulation from the drilling fluid. And for 30 meters, the temperature rocketed from about 350 to 900 centigrade. A lot of drilling fluid was lost, almost no returns of drill chips. So there was massive permeability. And at 2,100 meters, torque went right up, penetration rate went right up, and they got stuck in magma. and they couldn't understand what was going on. They pulled back and tried re-drilling, and they did this 3 times till they realized they were actually in a magma chamber. The key bit for me is that those 30 meters had monstrous permeability. And maybe we could envisage this magma chamber as being a bit like a hedgehog surrounded by a mass of if you like, basaltic columns as it's slowly freezing. And the fluid flow can flow in these gaps between the columns to give the massive permeability. So in the KMT, we're going to like to drill through the hydrothermal system, subcritical and supercritical, and then drill into the magma chamber to recover a sample. Now, how do you do that? Conventional drilling on the left is that you would drill down and the drill chips come up at the surface. Well, we want more than that. We want to get a physical sample. So we'd have to drill out a core. And the idea is that you just use a huge amount of water, and you pump and you pump and you pump, and you create, if you like, an icicle, a magma core from the top of the magma chamber, freeze it to a glass, and drill out the middle of this icicle, if you like, and recover a core. That's the plan. Just use huge amounts of water to extract the heat to quench the magma to glass. So it's quite challenging. We know it's possible to drill into magma. We've done it safely, but it's more a question of how do we protect the equipment, because it's extremely hot and aggressive, and how do we cool the drill bit, and how do we cut the core, and should we line the borehole to prevent all the fluids getting in, to stop corrosion? Lots and lots of questions. What if the bit gets stuck in the magma? What are the risks of a steam blowout? There's an image there of which used to be borehole KG4, which blew out in the early 70s and emitted an awful lot of steam, left a big crater. It's extremely difficult to drill in some of these environments. That steam loss actually sealed itself up quite nicely after a couple of years. The prize, however, at the end, if we can control these very powerful fluids, is really big, because we could get an awful energy. And that's why it's worth studying and investigating these things. So I've talked for about an hour. So about time I wrapped up. So to conclude, geothermal fluids, they've long offered this potential for renewable heat and power and help reduce our dependence on fossil fuels. There's great things we could do with them. The improvements in drilling technologies and materials, these diamond drill bits which allow you to drill faster, together with increased investor confidence that we can do this stuff, makes it possible to access resources in the UK, even this cold old country, cold ground of the UK, we can get the heat out. And Southwest England is at the leading edge of that. That's our new frontier in the UK for geothermal. And United Downs and Eden, together with some new sites, those are the sites where it's happening. But if we can combine revenue streams from not just power, from heat, from dissolved elements, from farming, from fish farms, from spas, this gives this cascade of uses of geothermal, and that makes for a better overall economic case. And we need to demonstrate that we can do that. And then on the international scene, this super hot geothermal, this offers a tantalizing prospect really of a game changer, this order of magnitude increase in energy per borehole. But the conditions down there present enormous challenges. We have a lot of things to learn. How do you drill into molten rock is really quite a big question to try and solve. So at the end of the day, we have a range of alternative energy systems, if you like, on the shelf that we can pick from, and geothermal is there and in the mix, and it's rapidly coming to the fore, I think, and it's going to be an exciting time this year, especially for the UK, when the first power plant is hopefully turned on, and that certainly will be in the news, and you hear about it. So that's it. Thank you very much. I hope that was all right.